So it is my absolute pleasure to welcome you all on this fantastic, beautiful Cambridge day into our Wulff lecture. Wulff lecture is probably the most important lecture in Material Science and Engineering department. It has been named after John Wulff, a really provocative and talented and inspired instructor, one of the really important members of our faculty. And here it is our pleasure to present Professor Alán Aspuru-Guzik. I hope I pronounced the name correctly.
Perfect.
Joining us and presenting his inspirational and provocative work on combining chemistry with artificial intelligence and machine intelligence and robotics, and how we can start using all of these fields together to advance science. Professor Aspuru-Guzik has started his education in UNAM, Autonomous University of Mexico, in chemistry, and then pursued his doctoral research at UC Berkeley and postdoctoral as well. He then moved to down the road at a school nearby, Harvard, where he has held a professorship for about 12 years until he had a change of heart and really amazing opportunity to move to University of Toronto and lead their efforts in computation and chemistry, and also their efforts in how this research can help environment, decarbonization, and so forth. He has founded numerous companies, and he has also a fellow of American Physical Society, American Association for Advancement of Science. He won numerous fellowships. The one that is important to us here at MIT is TR 35 from Technology Review. And I personally think that he did something very important for our community, and that's quite selfish, that he was actually a mentor to one of our talented, recently tenured faculty, Professor Rafa Gomez-Barbarelli. So thank you, Professor Aspuru-Guzik, for giving us your wonderful trainee. So with this, it is my absolute great pleasure to invite Professor Aspuru-Guzik into our Wulff lecture, and we hope everyone enjoys this scintillating presentation.
Thank you. It's a pleasure to be here. Yeah, over the years, I've been friends with many faculty here. Alfredo Alexander Katz and I have scuba dived in the Galapagos together. And then Jeff Grossman and I published my second paper with him as well. And obviously, Rafa used to be in our lab. So yes, many connections to your department. So that's why I'm not traveling almost to the US for reasons you can imagine. So this is an exception. So I'm very happy to be here to tell you about what we're doing in Canada. Today, I won't tell you actually too much about robots unless I have extra time for an epilogue. So I have an epilogue in my talk about robots. But today I'm going to tell you about AI agents, because we're all thinking about AI agents. So I'll tell you a little bit about agents. But what you see here is basically all the robots that we've been building in the University of Toronto Acceleration Consortium, which is, sorry, this is Alfredo's clicker. I have to learn how to use it. So the Acceleration Consortium is the largest grant ever given in Canada to a university, $200 million Canadian, that we actually use to build all the robots that you see there, and AI-driven materials discovery. From solid-state materials like batteries and catalysts, all the way down to organ on a chip. But we have a very interesting limit in the grant, because the grant is supposed to be for personnel. We cannot buy any equipment more than $300,000 Canadian, which is about $200,000 USA. And we can only buy very little percentage for equipment. So that made us very frugal, and all those robots that you see over there are extremely inexpensive. So if you want to learn how to build inexpensive automated labs, come to visit us. We're the masters of buying Chinese parts and Alibaba and all these places, and make very inexpensive robots. So, and this is a new building that's going to open in the fall. Right now we're distributed across campus, but we're all going to be in that building. That, believe it or not, is the first time ever in any university I worked at. It's on time. So November, come and visit Toronto. You will see our new Acceleration Consortium building. So today I will tell you about El Agente. This is unapologetically in Spanish. How many of you watch the Super Bowl Bad Bunny intermediate? So I come from Canada, okay? And I will tell you about El Agente, which means the agent, for those of you that don't know Spanish, okay? Everybody should learn Spanish, right? Okay, so now, okay, let's start with this, right? So like you see this image of little nice monkey on top of a pile of garbage, and you might have some empathy, okay, about the problem. Okay, there's garbage, right? There's a lot of garbage, you know. But if you actually see this person, and in my case, this is actually in Toronto. It's a stock photo, but apparently this is in Toronto, from as far as I can tell. So if I live in Toronto and I see this, I'm like, maybe we have a problem with garbage in Toronto, right? And then I look at it, and then now there's this picture of this garbage looking at our beautiful city, my city, and then I start feeling more and more empathic about it, right? So when I like to start giving talks, and I think this is the talk for the undergraduates about material science, chemistry, we always have to remember that we're here to solve big problems. For example, the circularity of plastics. So there's a student in my lab, Stanley, that is the only guy that's doing polymer science. We're trying to come up with a fully circular polystyrene recycling. So we functionalize it, and then we use light and like break it apart, and light and temperature, and then like we do it, right? So that's an example of something that we're doing in the lab, and we're gonna robotize. So those are the kinds of problems that I think we have to remember. We're here to solve the energy problem, pollution, health, etc. So that's what motivates me to try to accelerate discovery. Accelerate discovery to solve problems like this. So I was coming here, so I was trying to find out all the pollution that happened in Massachusetts. I used to live here for 12 years. And I found a website that had tons of them. This is an example one in Foxborough. I think that's where the stadium is, right? And there's all this, you know, horrible pollutants there in a former factory that it took forever to clean up, right? So we have these problems everywhere. And I think the new generation here, the students should actually think about these problems, how to solve them. And it's only one environment, one earth, and so on. But now I came here to talk to you about machine learning and AI and automation and materials. So why don't we get into it? So a couple years ago, together with the group, we wrote this Faraday discussion. It's a very interesting conference. Has anybody gone to Faraday discussion? It's a cool conference because everything that you say is recorded in a dialogue that you can read later. So-and-so said this. So-and-so replied this. And they send you the transcript, and you're supposed to edit what you said. So sometimes if you said something stupid, you can retroactively fix it. So we all sound very smart, but you can download the Faraday discussion. But I was the opening speaker. I was supposed to tell them what's the status of the field. So I really enjoyed writing this paper, where we started to think about all the problems in chemistry, and they're very similar to the problems in material science. Obviously, in material science, you work at much different scales than us, and time scales and so on, and problems, but more or less it's the same physics. And you can see here all the chemical or material science problems, and then some of the algorithms from machine learning that you can combine with them. So we wrote this table, and we were very happy to see kind of all these connections, right? For example, the Monte Carlo method, okay? Sampling from a Boltzmann distribution, this my friend said there. Sampling from a Boltzmann distribution is a problem that we have in machine learning as well. And at the time I wrote this paper, this review paper, we wrote this thing here called agents, okay? And the group was still not in the space of agents, okay? But how many of you are undergrads? Raise your hand if you're an undergrad. So in Toronto, we have like MIT-style undergrads. They're part of our engineering science program. So we call them the MITs of Canada. So they're amazing, okay, these engineering science kids. And also the Waterloo kids, right? They're supposed to be equal or better. We say we're better, they say they're better. So I got this kid from Waterloo. His name is Jackie. And he told me, I built this agent to control our robots. Look what I built. And I was like, holy shit, like this is an undergrad, okay? So I said, okay, Jackie, this is amazing, but do not connect it to the robots because this is dangerous. Like it could make an accident. I was just traveling and I just found out there's this lab in the UK that exploded because an AI was controlling the lab, did an experimental setup that was not correct, and the lab literally exploded. So I don't want that to happen to us. We don't want to connect an AI to the physical world yet. Let's use the agents for the virtual world. And it coincided with the fact that Professor Vanilla Bernales moved to Toronto, and we started to co-lead the lab, and we said, let's pivot. Let's take 80% of the lab and all do agents, okay? Agents are so amazing. Jackie and undergrad convinced us we have to change all our entire research and build agents for science. And that's the story. So this is a year and a half of adventures building agents. So I Googled what the heck is an agent, okay, like the definition. And actually, the best one came from a blog post from OpenAI, okay? The one that I like the most. I don't necessarily like OpenAI as much, but I like this definition from them because it's very simple, right? An agent is an automated system that can accomplish tasks on behalf of users. That's very simple, right? That's an agent. So why would we like to build agents for science? Because, I mean, maybe we like to do those tasks. But how many of you have tasks in your research that you don't like? Raise your hand if there's a task that you don't like in your research. How many of you keep your hand raised if you want an agent to do it for you? Right? How about if you don't want the agent to do it for you? Raise your hand. A few of you, of course, there's said, for example, there's resistance, obviously, also to using these agents, right? I mean, they are these weird things. So how many of you have used an open claw? Raise your hand. You don't have a claw, you have a claw. It's incredible, right? So one of my students, I always learn from my students. One of my students, his name is Luis, he comes from Colombia, got his claw, okay? And he started showing me what his claw was able to do, okay? So I said, I immediately want a claw, and we bought 5 max for the lab to have 5 claws. Mine is called Clotilde, okay? And you know, these claws are great. They can do a lot of things for you. And they can be evil, they can be, as you know, you cannot give it any personal information. They could delete your files, they're very dangerous too, okay? So these are the 2 sides of the internet. What I really like about this clause is that you put it in your local file server, you connect it to your WhatsApp or to your Slack, and you can chat with it and give it tasks, right? This is a quote from Jensen Huang. So I work half-time at NVIDIA now, which is another weird thing for me. So I'm half-time at the University of Toronto, half at NVIDIA, so I had to show you a picture of Jensen Huang, I guess. But seriously, I just saw this news. He's saying OpenClaw did what Linux did in 30 years in 3 weeks. This is the most viral software ever. I think the number of GitHub stars and installs of OpenClaw has gone exponentially bigger than any software ever in history. Okay, so I think next time I will come, all of you will have a claw. Okay, so I was very skeptical about this, but so this is a picture just to demonstrate that it's true. I told the claw, okay, you know, go to the internet and find me papers that are related to what my research is. Give me a summary every day, and then Luis asked it to make a CSV and check at 5 p.m. every day or whatever it is, right? And then that's it. You can tell it that in English or in Spanish, and the claw will start actually doing it. So why am I telling you all of this? Well, in principle, right? In principle, we can imagine that these things could eventually one day make scientific discoveries, and they might be able to be interesting co-workers or tools that we can use to actually learn about science. And that's been the journey that we've been working on. So by the way, the colors that we picked are also Latin inspired. This is the Mexican architect Luis Barragan. Okay, so I'm tired of all these grays and stuff, so it's Mexican colors, okay? So basically this is kind of like our tagline. Like, if you really think about research, most of the time it's a human that decides to go to sleep because they're tired or go to watch Netflix or whatever, right? We're humans, we get tired, we have to drink Coca-Cola, I don't know. But a machine in principle could go faster. So how can we accelerate hypothesis generation and validation? Democratizing access to science is very important to me in particular. There's a lot of barriers to science that you don't see, but some of the things that we do as computational chemists take forever to learn, entire PhDs to learn. And maybe if we have an agent do those things for you, you can actually expand computational chemistry to all chemists. And therefore, chemists can do computational chemistry without the barrier of learning how to use these horrible codes. So for me, this is actually the most important, actually, democratization. So we want to make scientific discovery accessible to all, and we're building a platform that is going to be non-profit for all of you guys to play around. And this clicker of Alfredo. So what is an AI scientist? So the AI scientist will sit down and come up with a hypothesis. We'll lend this talk to some of the work that we're doing to generate hypotheses. He goes away and does computing or experiment. And I showed you we have tons of robots at the beginning of the talk. I show you all these robots. Again, we are not connecting to the robots out of safety, okay? Not because we can't, but because we want to be slow at doing that, okay? And I can tell you more about what are the cool things you can do to actually stop Armageddon in terms of chemistry, right? Like, for example, how you can generate processes in the robot that are not going to generate phosgene gas or are not going to be dangerous to the human in some way. I was just talking to Alfredo. He told me that he was connecting an AI to one of his machines, and he was worried he was going to spill out liquid in his lab. I said, that's okay. Spill out liquid is not as bad as killing a person, right? That's the problem I'm worried about. So computing or experiments. So I want to tell you more today about computing. And then the interesting analysis piece, right? How can you analyze the data that came out of the computer in an automated fashion and then decide what is the next experiment, right? So that's kind of like the cycle of being an AI scientist. So now it exists already. So El Agente, which we started building with about 40 people in the lab for about a year and a half. So this is about 60 human years of work. Again, we pivoted the entire lab and we said, now we're all working on agents. But I do quantum computing. Well, you work in the quantum computing agent, my friend. So we have a quantum computing agent, right? Called El Agente Cuántico, and so on, right? So basically we have this place where you can chat with it, imagine ChatGPT, but you also have side windows that can visualize molecules. You can click on them and do things to them. And then you can generate reports that are in PDF. They look like a paper, basically. Okay, and this is an example, actually. I put it here for Rafa because Rafa and I co-founded a company called Calculario. And what Calculario was doing in Boston is doing some type of calculations that roughly a scientist took 2 weeks to do. Because they had to edit the file, send it to the cluster, analyze it, put it in a table, show it to their boss, etc. So if you figure out how much that cost for an engineer, that's about $15,000 USD. It cost us $25 to just send it to the cloud 18 hours later, 200 interactions later. It does that task, and that task arguably is kind of one of those tasks that if you do 200 times a year, you're probably not that excited about it, right? If you keep doing that, it's not necessarily what you want to think about. You want to dream about new materials, think about new ideas, not necessarily run this computational task over and over again. But this is what many scientists in companies are stuck doing. They're verifying some hypotheses from their experimental colleagues, and they're just running these calculations. So this allows people to be more creative, in my opinion. So this is the team. Okay, as I tell you now, co-direct the lab with Professor Maria Bernales. I cannot do it otherwise. We're too many people. This is our system administrator, Chris, that is very important because he's the one that sets up all those open clauses and makes sure everything runs on the cloud, and so on. All these people have played many different roles, but I mentioned Jackie, so let me find Jackie. He's the one that started it all, and here is Jackie. Okay, he's the one that started the whole adventure. Okay. So now in our papers we talk about 3 different types of. How many of you have used Siri or Alexa, one of those things? That's an assistant, right? It's pretty stupid, right? Siri doesn't even understand my Spanish accent, so I'm like, Siri, play this playlist, and it doesn't understand the playlist, right? So like my accent is a problem for Siri, okay? So, but then you have collaborators, and we're at the level between a collaborator and a scientist in our lab, okay? So a collaborator would be somebody that you can ask it to do that task, like the one I showed you before, calculate the excited state of this molecule, plot it, compare it to this other molecule, right? A scientist will be able to generate a hypothesis, think about something new, right? Go ahead and surprise you with some new discovery, right? So we're almost there. I'll show you some glimpses of that. But I would say right now we're at the level of a PhD collaborator. So somebody with a PhD that does something quite complicated, but that is routine, is not necessarily going to blow your mind. That's the level that we are with our Agente agents, which I hope to have in a couple months in the cloud for all of you to use. Scaling and software is very hard. So I'm going to tell you our first version is called El Agente Q, El Agente Cuántico, okay? Agente Q. So this is the agent for quantum chemistry. This is basically our OG agent. The first author is Jackie. You can see his name there, Jackie Zhu. And basically, how does an agent system work? So a little bit about it. So all of you have used an LLM, I assume, and you go and chat, and you know there is a context. And the context of an LLM, it can be a certain number of characters. But then it gets full, because basically, the cost of these calculations, naively, is the square of the number of characters that you give it. Okay, so you want to have more RAM and more compute and so on, scaling as the number of context tokens that you give it. Okay, so the models obviously have tricks to scale better and better as the number of tokens, but sometimes when you use those tricks, then the models get confused. In other words, like a human, if I give you tons and tons and tons and tons of information, right? For example, I took a test to become Canadian, okay? And the test was a test in English that said, that man was dressed in red and he was giving a talk and so on and so on. And it kept going and going. It says, what color was the man dressed? So I was like, this is an unfair question. I thought they were going to ask me about this complex arc of the story. And they were asking me about a stupid detail, right? So that's the problem. If you ask an LLM a detail, sometimes it will hallucinate. So the way to mitigate that is to actually have these very strict contexts that reveal slowly to the agent only the important thing that it cares about. So in our strategies, we have, it's kind of like a company or a department. Paulina, the department chair, says, head of this committee, go ahead and do that. And the head of the committee tells the grad student, who tells the undergrad, right? And then the undergrad does it. And that's how universities work, right? So undergrads do everything, and then there's this channel of like command and control, right? Especially control. But anyway, what is interesting about this is that the bilateral communication between the manager and the sub-agent, right, has to have certain rules and certain disclosure of information. You don't want it to know too much, and you don't want it to know too little. You want it to know the right amount to do their job correctly, okay? So that is how you handle these things. You have a collection of these guys that have memory, like it's called episodic memory. They remember previous episodes. They have also semantic memory, which basically means what am I supposed to do? Who's my boss? Who's my dependent? And what can I call and what can I do? And they have access to tools. And that's what an agent system is. The most powerful one is Cloud Code. How many of you have used Cloud Code? It's a very powerful system. What we build is extremely similar to Cloud Code, but for science. Okay, so actually when the Cloud Code blueprints came out, they were side to side basically what Jackie had built. We were very impressed because it's the same idea, but instead of coding, we basically built it for science, kind of like before the blueprint of what exactly Cloud Code was doing was. So this is our very early GUI. Our GUI is now much more beautiful, but this is very important. Calculate the ground state energy of caffeine. This Coca-Cola has caffeine. Everybody should do that. That's already a pretty hard problem. Look at this. This is where 20 agents, they talk to each other. They send information back and forth, create files in the supercomputer, download the stuff from the supercomputer, visualize it. It's not trivial to do all of that, right? So this is the first kind of like hello world that we had in the lab. And you can see here all the stuff that we had there to debug. Stop the chat, view the chat memory, manage the memory, do this and that, right? So we started learning how to build these agents, and then eventually they started doing more and more complex things. So that's el Agente. But even our original Agente is very impressive. So how many of you have taken undergrad chemistry class? That's great. So you guys can probably solve this problem. Okay? Compute the values of the enthalpy and the enthalpy and the free energy for the following cyclization reactions, right? So you have a cycle, and then the CH3 just, so you have a cycle like this, and now it's like this. And the question is, okay, compare the ring strengths as the carbons become shorter. If you really think about it, there's a lot of abstraction that comes here, that comes from the fact that these models like ChatGPT or Claude already know a lot about chemistry, but you actually implicitly can give it things like this, right? This is basically what we give it as an input. And it aces questions like this. So we're very happy that in El Agente, we are the only group in the world, as far as we know, that always benchmarks every agent that we publish. So we spend a lot of money on that. Every paper is about $5,000 to $10,000 worth of credits. And what it's all about is about the benchmarking of like, okay, run this experiment for 10 times, and let's see how many times does it do it, and how many sub-tasks did it fail at. So we have a rubric like grading, and there's grade inflation. Obviously, you guys here in the US, you're experts at grade inflation. In Canada, we have less grade inflation, but you guys have a lot of it, and then Harvard has even more, I guess, right? But the point is like, you can imagine we have also grade inflation, so our agents do 96%, 97%, 80%, whatever. That doesn't mean too much unless you see the rubric. But usually our agents forget to give you one number. You tell it, give me 10 numbers, and it gives you 9 numbers. So you give it 96% based on the rubric, right? So within those rubrics, El Agente is about 95% efficient. So there's about 5% of stuff over number of runs and number of things it does that it will forget to do. And the way to fix it is to prompt it and say, Agente, you forgot to tell me this, right? Or Agente, this is wrong. So there's a human intervention for about 1 in every 20 times. So now, I'm going to show you the second version of the Agente Cuántico. This was developed after a year. Tons of people. This is now Juan, a postdoc from Colombia. So we named it Contour, which is the name for the condor, you know, the South American bird. And the reason we had to use Contour is because Condor is the name of a US operation to dethrone Agente in Chile. So they really took it for something bad. So we had to go to the Quechua, you know, and use the original word for condor. Okay, so yeah, be careful when you name things, because if there's a CIA operation named after it, you should not use that name. Okay, So this is, yeah. Exactly. We use the Q for that reason. Yes, it's the quantum condor. Yes. So anyway, the quantum condor is awesome because it has something new. We give it the manual, okay? So we reorganize it in a very interesting way. We have experts on different domains, and we give them the manual and we give them papers, okay, for that particular thing. So like imagine that you want to learn a theory, and there's a nice review paper by a fancy scientist. So you can give it that and say, you expert on this subsection of the code, you have to read these papers to actually be very good at it. And these sections of the manual. And this Reddit file, Reddit actually, you can go there and like search what the users were saying there or in Substack or whatever. So this is very cool because it goes to these places and reads information about that, has access to the tools, and therefore El Agente Contour basically covers all of ORCA, which is the quantum chemistry package, and it's all helper packages except QMMM, if you guys know what that means. We didn't have time to do this quantum mechanics, molecular mechanics stuff. That's the only thing that we haven't tested. It probably does it, but I told Juan, okay, Juan, let's just publish the paper. Like, forget about that. Let's publish another paper about that. There was too much stuff going on there. So now you can see here 60 agents. The average number of interactions for a PhD level problem is about 200, and it takes about 20 hours to do. Because it will go to the computer, do a calculation, go back, do another one, go to the cluster, go back, analyze, generate a PDF, generate energy level diagrams, reports, etc., etc., etc. So in some sense, after a year, we went from what we call an undergrad to a grad student. Okay, so I think Contour, from the examples that you will see on the paper, are really basically PhD level problems. One of the problems that we gave to Contour, I had a student that we gave the student that problem, and the student left the PhD because they couldn't do it. We gave it to Contour, and he one-shotted that problem. Okay, so that's the level. Okay, so now let me tell you my favorite. I have many favorite agents, but let me show you one of my favorite agents, if you don't mind. Estructural, the structural agent. We find that the biggest problem for chemistry and material science probably is analyzing the structures visually, right? Like these things will fail a lot because there are these things called SMILES. How many of you know what is a SMILES file? Raise your hand. You know, there are sequential files that represent a chemical structure. They don't have any information about 3D structure, conformers, anything. So when you try to automate these things, when you convert SMILES to 3D, that's a big failure mode. So agentes usually fail by this representation of language to SMILES to 3-dimension, right? So what about using, how many of you know visual language models? Have you heard about that? Like basically language models that also look at pictures, right? The ones that you can narrate like, oh, this is a cat sitting on a table, and you know, all of those things, right, are teaching, especially Google Veo and other models, they're teaching the spatial world to these models. So because you are basically using multimodal, multi-perspective views, you're giving it textual descriptions, all the YouTube videos and things like that, these things start to understand that there is a ball on top of this table and the ball is next to a Coca-Cola bottle and like so and so on, right? So can we use that for molecules? So basically, we render the molecules to the LLM with numbers on the atoms and certain colors and shapes, balls, to make it easier for the model to see the molecule. So we have to kind of change the rendering style so that the model can know which atom is which. Like, okay, this is 1, this is 2, this is 3. And we show it several perspectives. And we have external tools. We took a molecular editor, Gauss View, and we asked, basically we built a Python package for each one of the things that Gauss View can do. Like, okay, change this group by this other group, rotate this bond, change this dihedral angle. All of those things that people do by hand, all of them made a script for. By hand in this case. Like get atom neighbors. And we gave it access to, we gave El Agente Estructural access to all those tools. Together with the vision, these things started doing amazing things. Let me show you one of my favorite examples, okay, of all time. There is this molecule called sumanin, okay? So you can imagine having a metal binding on the top of sumanin or on the bottom, convex or concave binding. So you tell it, you can read there, can you please give me the concave binding or the convex binding? Okay, cap it with a ferrocene. Put some ferrocene there. Or cyclopentadienyl, I think it is. Yeah, and then like, okay, I don't like it that it was bound to the center of this molecule, put it on the side. And we are like, our jaws open, right? When you see that once you give these tools to these AI models, then they become more powerful. So now, I am originally a computational theoretical person, so I like to think about theoretical scaling arguments. So I'm going to make you an argument. And let's see if somebody can. We're in MIT, somebody should know this. How does the power of an agent grow as the number of tools it has? Just think about a theoretical argument for that. If I have an agent with 10 tools and an agent with 100 tools, how much more powerful is the agent with 100 tools? Just guess. So if the tools interact with each other just pairwise, right? This scales as the square of the number of tools. Okay? So that's just, of course, a lower bound, because in principle, tools can interact in 3 body ways or 4 body ways. And of course, it could be that the interactions are sparse. So this is empirical. But just as a computational chemist, I think in matrices and scaling, and it's roughly quadratic with the power. That's my hypothesis. You can call it the Aspuru-Guzik law, right? The power of an agent grows quadratically with the number of tools, okay? So we're building many agents with sub-agents. Each one of them has access to many tools. So we're building this monster with many more powerful capabilities. So in this case, we gave it all these molecular vision and editing tools, and it impresses us. For example, we cut and pasted this from a paper. And we told it, look at the reaction in the figure and build a substrate and product with R on the C alpha to S as methyl and the others as H. Okay? It makes the substitutions with those tools that I told you about. Can you generate the possible transition state for this pathway? And then we have a constrained XTV quantum chemistry calculation, constrains a bond, relaxes the molecule, generates a transition state. Then the human interacts and says, you see, I told you that 95%. Sometimes you have to go in there and say, hey, dude, the CN distance seems too long. Okay? And I have a postdoc called Kenko that calls the agent bro all the time. I don't know why, but he would say, bro, CN distance seems too long. So I'm like, dude, that's too sexist. You should call it something else, right? But he keeps calling it bro. But I just call it dude or something like that. So CN distance seems too long, and then I forgot the contraction, and then does it. I'm not claiming, for those of you, how many of you built a transition state by hand? I am not claiming that this thing can do all transition states. But Jackie took on his PhD to do transition states. He specialized in that. He's now an intern with me at NVIDIA, and the only thing he's doing is building transition states, probably for the end of his PhD. So maybe by the end of Jackie's PhD, we'll have an agent that can build transition states for everything. But he got so excited about it as a computer scientist that he now knows more about transition states than chemists. Okay, it's incredible. So now let me continue. This thing doesn't move. No, it's the lab. So now, these calculations cost about $25 per calculation. So that's a lot of money, right? If you think about it, run 1,000 molecules, that's $25,000. So obviously that doesn't scale, but obviously we have workflows. We always think in terms of workflows. So you probably want to have something that if it generates a workflow, the workflow can be exportable, and you can apply it for free to the next set of molecules. If it's something boring, you want to just duplicate it many times. But also, maybe you want to think in terms of workflows all the time. So what if we have a planning agent, we call it el agente gráfico, that builds an entire workflow and puts sub-agents inside of the workflow and says, you know, this is a workflow and this is a decision point, so I'm going to place an agent in that decision point, okay, for the future. But this planning agent, a single agent, plans the entire thing before. It's a different strategy, okay? In this talk, I'll give you 3 different strategies to build agents, okay? This is strategy number 2. So about half of our agents use the graphical strategy, half of our agents use the original strategy I told you. So in our group, we have conflict, actually 2 camps at least. So people sometimes start and complain, say graphical is better, the other guys say the other one is better. I let them fight intellectually because we really have a lot of fun trying to figure out which one is better. So about half of the group believes this is a better idea. How many of you know what is pedantic? Pedantic means pedantic, okay? So it's like Python that is pedantic. So it means all the types are very well defined and everything is well known and this depends on this and so on. So if you are very anal, you will like graphical because graphical is the anal agent and the other agent is very free, okay? This one has to have everything ahead of time, routes it, and every once in a while, something very important happens, which is you do not pass things to each other via the context as the other agent. That's what makes it expensive. But because we use pedantic, we can pass Python objects directly between the different states of the agent. So therefore, you can only pass it very little amount of text. So it's very cheap, okay? To the point that a calculation in graphical probably can cost 3 cents or 5 cents of GPT time. And the other one costs $25, okay? So for about 10 cents or something like that or whatever, you can do the same thing as $25. And there's certain trade-offs, but basically for things that are more workflow-like, el agente gráfico is very powerful. And for example, here we're asking it to build metal organic frameworks. How many of you like metal organic frameworks? Okay. I don't know why people like them so much, but I mean, my postdoc says like, I want to do MOF. Okay. The reason I'm saying that is that everybody does MOF, right? So this is an example like for the masses, okay? All of you guys that raise your hand that like MOF, well, this is just for you, okay? So build the raw topology MOF with the metal node N153 and organic linker E21. Boom. Graphico is very good at doing things like that. And then you can run the quantum chemistry calculation. This is a different GUI. If you can tell, it's more beautiful. So our GUIs get more and more beautiful with time. So this is the GUI for Graphico, and then you can export the molecule and so on. So it gives you an idea of the kinds of things that Graphico can do. You can see that. But I think it's a very powerful agent because it's really well structured and it's very, very flat. So who knows what type of agent is going to work? But now I'm getting to the final family of agents. This is the most crazy agent. It's forjador, the forger. Okay, like in Minecraft. How many of you have played Minecraft and you forge a tool? So it's inspired by Minecraft. You make a tool. So in this one, it makes the tools on the fly. Okay. So here is the forjador. You can see it forging the tool there. And what it does, it goes to the internet and says, "Dear internet, I need to calculate the energy of a molecule. What tool can I download to do that?" And internet says, "You can download this tool from GitHub." And el agente forjador is very, very brave. He goes and downloads it. You can imagine the security problems there. Okay? You could download a virus or something, but agente forjador is try to be as secure as possible, downloads it from the internet, installs it, builds a Python code to run the tool. And the philosophy between forjador is different because what CGen likes to say is give forjador a set of questions. And the only thing you want to assemble is a set of scientific questions. And the more scientific questions you add to your database, forjador will be able to build and build more and more tools that it generates, evaluates, and then optimizes. So we have 4 agents. So there's an agent that builds a tool, an agent that verifies the tool, optimizer of the tool. For example, if the tool is repeat, you will remove it, okay? Or merge it, or you see what I'm saying? Because it can go out of control. Let me show you. We actually took our Quantico, our quantum computing agent, and our quantum chemistry agent, and we gave it the same problems that these 2 agents were able to build. And what it did is start building all these different utility functions, puts them in a file folder. And this is where the semantic memory is now. The semantic memory is a bunch of scripts in a file folder. So this is very similar to Cloud Code, and actually uses Cloud Code as its backend. So forjador, we think it's very important if, for example, you ask me, Alán, solve a climate dynamics problem. I have no idea, like I don't work in weather simulation. But I could ask forjador, bring it on, okay? And if you don't believe me, here is, for example, doing all this quantum computing stuff. Tensor networks, you know, the imaginary time evolved, Gibbs purification algorithm, Hubbard observables, etc., right? There's a lot of quantum computing stuff here. This is one of my favorite examples. El agente cuántico, we ask it to do what is called basically stir up. It's basically a quantum control technique to pass quantum state from A to B through an intermediate state. You have to shape the pulses with something called grape and optimize some pulses, then send the pulses to this quantum system. This is how the pulses look like. And it does these oscillations and eventually transfers the population. So we told forjador to do it, and then forjador came up with this. And then the postdoc said, I said, I'm an idiot. I said, like, you know, Nacho, it's wrong. Look, this has more oscillations than this one. And Nacho told me, what's the problem? He transferred 100% of the population. The task was to transfer 100% of the population. You didn't ask it to minimize the number of oscillations. So it's just, you can see how 2 different agents with 2 completely different philosophies did the quantum control to transfer the population. I didn't give it any bounds of how we should do it. So the agent figured out how to do it on its own in a different way, but it's the correct answer, right? So this is forjador in a single shot, downloaded everything from the internet and did it. And this is Quantico, a more handcrafted agent for quantum computing, okay? So now I'm gonna try to end this talk because I have 5 minutes left or so, I think, before the questions, because it ends at 5, right? So with all the agents that we're building, so how many of you like solid state simulations? Okay, so download Agente Solid. Well, actually, no, you cannot download it. We don't give you source code. we'll give you access to our platform for security reasons. I don't want you to use our code. Okay? So Solido, it will be in our platform very soon. It's for solid state calculations. It runs Quantum Espresso if you like that package. Graphico is the one that I just told you about. They just came out in the archive. But we have many more coming. The drug discovery one is called Pharmaco. The quantum computing one is Quantico. It's already in the archive. I don't have time to tell you about it. And also, I think you don't care too much in the material science department about quantum computing. Teorico is not. I'll show you a slide about Teorico. Teorico is the one that derives equations and actually tries to do theory. This is a chemical safety agent for obvious reasons. I don't want to explode the lab. El agente seguro. And then we also have a machine learning potential one that makes agents talk to each other. I will tell you about Creativo. And this is a Bayesian optimization one. So those are all the agents we're building that I can disclose today. We have more. This is, for example, Potente. Potente is a machine learning potential one. I'm in the material science department, so I pulled it up. It's going to come out in the archive in about a month or so. Can you run MVT using molecular simulations of the lithium phosphate for 2 picoseconds using matter sim, blah, 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 and there's your lithium phosphate battery, whatever, right? So that's just, that's just what it's doing, okay? This is the guy that calls it bro all the time, by the way, Kenko, the first author of this one, calls Potente bro all the time. This is the drug discovery one, Pharmaco. Is there anybody from Boltz here? You guys know or friends of the Boltz people? They raised $26 million, they said, to make an agent for Boltz. And that surprises me because we just built an agent that uses Boltz as one of our hundreds of tools. So we basically use all of the NVIDIA NIMs. Because I work at NVIDIA, we use all the NVIDIA NIMs for BioNeMo. Anything that NVIDIA BioNeMo NIMs do for drug discovery are in our drug discovery agent. So we can ask it to do campaigns for like ligand discovery and optimization. And in this one, we already have run robotic experiments to validate what it's doing. So that's our drug discovery agent called Agente Pharmaco. And this is Teorico. Nacho is a quantum computing guy that came to the lab and built Agente Quantico for quantum computing. And then he came one day to group meeting and told us Teorico. So this is a story that involves my friend Seth Lloyd here. That's why I invite him to the seminar. I have a paper with Seth. When I came here, I didn't know anything about open quantum systems. And I entered the field of open quantum systems. So we had this postdoc that used to work with him as well, called Masoud Mohseni. That is a pretty heavy Iranian guy that explained to me over 3 blackboards the Lindblad master equation. So he derived it for me. I have the pictures. He and Patrick Reventros, which also work with us, derived everything. So we asked El Agente Teórico to derive this equation. And obviously you can say, well, of course, it's on the internet. Well, it's on the internet, but what we do here is we use SymPy to verify that every step along the way is correct. And we have so many checks and also numerical checks that whatever it built is actually correct. So it not only builds the equations, but also builds numerical test codes to test if the equation makes sense. If it conserves particles or if it conserves the positivity of the density matrix or things like that. Okay, so this is El Agente Teórico. It's in preparation, and Nacho is already throwing it at problems that we don't know the answer. So the hope for the Agente Teórico is that we're at the edge in quantum information. We don't know the answer. So we're going to just ask it to do something that we don't know and spend a lot of time verifying it and then publish. We're almost there. It's already did 3 things that we think probably are going to work. So that's El Agente Teórico. And what's behind it is basically SymPy, which is a symbolic verifier that we use to verify all the equations that we generate. And this is the craziest one. This is Creativo. So CGN is thinking about the following problem, and this is where I end my talk telling you about Creativo. What is a paradigm shift? Okay? So CGN is very ambitious. It says, like, how can I come up with an agent that comes up with a paradigm shift? How many of you have read about Thomas Kuhn and scientific paradigms? Right? So the idea is that there's some idea that changes all the way you connect your concepts. Right? Somehow this new idea changes the way you thought science was supposed to be working. So we are building an agent that is trying to build paradigm shifts. So this is basically what we have. We're getting a chemical reviews paper on what is called chemical representations. Right? So all the possible representations of chemicals in the computer. You have here all the representations and then the operations and connect them. So you have a graph that says this is a chemical representation like smiles. I don't know if you guys know we developed one called selfies, but that's selfies. How is smiles and selfies connected? Or how is like the latent space of an autoencoder connected to this or that? So this is kind of like the map of how any chemist or material scientist could represent any molecule. And then we ask Creativo things like, okay, what are the most disconnected nodes? What would be nodes that connect two islands of ideas? What if we try to replace all these 5 things by a single one, or things like that? So we're trying to break this network in some way, try to generate ideas and brainstorm them in a way that this network changes, and that's how we're trying to create creativity. Maybe we're going to fail miserably, but this is what we're doing right now. I'm disclosing something that is not published or anything. We're starting this project maybe for a couple of months, but I wanted to show it to you here because I have many friends here. This is Creativo. And obviously this is a cool visualization of how Creativo looks inside, but Creativo is doing many other things. And basically this is our biggest problem is how can we make a platform that if all of you connect at the same time doesn't crash? That's what we're working on. That's an engineering problem that I'm not very well equipped to do. But these are a lot of the agents that are coming out. So to end very quickly, philosophically, if we go back to philosophy, I argue that we're all cyborgs. How many of you use your phone at least once a day? When you're on the toilet, keep raising your hand. Okay. So we're cyborgs, right? We're always like walking like idiots, like looking at the map, right? Even if I know, I used to live here for 12 years, how to get to Seth's office and building, I still look at it, right? Because I'm like, is it this way or this way? Like I completely became a cyborg with my Google Maps, right? Or my WhatsApp. But one day these machines will become androids. They will become independent and they will disconnect from us and they will be doing their own things. And I think we're getting there. And it's a philosophical question. How does it look to talk to an android that does science together with you? I don't know. This is going to happen sooner than we think. So that takes me to the end of the talk where I have a quote for this. So what is the role of the scientist? Well, this is a poem of Jorge Luis Borges about chess. And Jorge Luis Borges wrote this poem about chess where he says, God moves the player and he the piece that starts this game of dust and agonies. I'm paraphrasing whatever is there, right? But basically, we are the ones that build those agents. So at least we get the pleasure of building those agents. That might be our role in life. And with that, I'm going to end with a picture of our research group. Here is Varinia, the co-conspirator of it all. Here is Jackie, Sijian, I mentioned some of them, Austin. And a lot of these people build these agents. We photoshopped some of them in the back, if you can tell. This is Marcel, looks very photoshopped. And with that, I just want to thank you and have some time for questions.
Thank you so much, Alan, for this scintillating presentation and indeed quite provocative. So it is our pleasure to open this for questions. And I would like to first let our undergraduate participants to have an opportunity to ask a question. So if you are an undergraduate and you're itching to ask Professor Aspuru-Guzik a question, so now is your chance before it becomes a free-for-all.
And the first one gets 20 Canadian dollars as a prize.
Here we go, the stakes went up. Make it good.
I will donate to you 20 Canadian dollars.
So in cash.
Yeah, in cash. I still use cash in it. North of the border, we still use cash. In case you invade us, we need to have some cash. Okay, who wants some?
Let's do it. Here we go.
Okay, so what's your question? And then come get your 20 bucks, okay? Because you're too far away.
Hi, thank you for your talk. My name is Isabel. I'm an undergrad. I'm currently researching like MLIPs, and I'm wondering how your models integrate like DFT data or MLIP data. Do you actually run those calculations, or do you use existing data in the literature?
It's a good question. So we divided it in the following way. The way you want to think about it is we have an agente called Diplomatico that is built to have all the agents that we have built together. Okay, but at the moment, we have Kenko doing all the MLIPs under Agente Potente, and he's focusing mostly on material stability and questions like what is the convex hull of this material, or like calculate the delta G of this. And you know, it's very focused on stability, just because there's so many agents from MLIPs that we wanted to have something unique. And then El Agente Cuántico, Contour, they use quantum chemistry calculations. Although sometimes they can call the machine learning potential to relax structures. For example, Solido in particular, our solid state one, when it's sometimes it calls UMA, if you know that force field, to optimize the geometry first. So sometimes our specialized agents have access to force fields, but we build an entire force field agent as well. And there's redundancy there, obviously. Solido can build moth, but also graphical, and so on. So we take care of that later by Diplomatico. Diplomatico is the one that asks everybody, what can you do? It's a diplomat, right? Okay, should I give the problem to you, and why, and so on. And that's the one that we're building to have all the agents interact with each other. So it's a pyramid of many agents that have sub-agents that have tools under them. So the answer is complicated, but I think that's how I can give it to you. But we don't fit new potentials yet, if that's your question. So we just use the ones that exist. But maybe you can come in the summer and build that tool.
You get a job too, not only $20.
Well, maybe she has to apply, but you get $20 at least. Yeah.
So now we can move on to our other questions. So if we have any more undergraduates, if no more takers for $20.
No, I always only one.
Okay, sorry. I thought there is free money. So then we open
Can
our.
I be reimbursed? No, just kidding.
This is.
Just kidding. Okay.
So anyway, so now we'll open a question. So please go ahead.
Okay, thank you, Professor. So I got two questions actually. So the first one is like in general, from all the agentic systems you have built, can you like share some of the design principles? Like how do you break down a workflow into, for example, how do you design the architecture of your agentic systems? Like how many agents do you need? Or why, like you show the graph connections between all the agents, like how do you come up with those designs? And yeah.
So let me answer very briefly. So I tried to show you three philosophies. Okay, number one is forjador. It thinks that the role of the agent is to build Python scripts that do things. So all the information is in those Python scripts. So forjador is an agent that builds Python scripts. Okay, so that's one strategy. You have a hard disk full of Python scripts that do things, and that's the forjador style. That's number one. Second one is graphical. Graphical uses pydantic, and pydantic is like this fancy way of describing dependencies between data and execution. So it will generate this execution graph and then execute it. That's style number two. Style number three is a LangChain style where you handcraft and you say, well, I should have a computational chemist and it should have an input file handler, it should have this. By hand, our humans start building their sub-agents and testing it. So the lab at the moment has three philosophies, and we have vibrant debates about which one is the best. It's all on the papers, and I will argue the three of them are more or less equivalent. So as a PI of the lab, I usually laugh at the passion of the grad students and postdocs arguing with each other about things that get more or less the same answer. They all get 95% accuracy. So like at the end of the day, there's many ways of skinning a cat, and I think the three strategies that we found that work are already published. Forjador is about to be published, but you can email us and we can give you information about Forjador.
Can I get one more?
Yeah.
I think we'll limit to one question, so because I can imagine how this is very popular. So let's go to you.
Thanks. Hello. Oh, hi. Yeah, really nice talk. I was just curious, what happens if you give your agents a system that's like underspecified? So you used the example of ferrocene earlier. Based on the oxidation state, you can have a different charge, different number of electrons, different spin states. If you just tell it, like, optimize the geometry, will it make assumptions and disclose those assumptions? Or if you give it something that's even like ill-posed, will it tell you that that's an ill-posed?
Yes. Okay. Yes. So we have one of the examples that we have is lanthanides, which have tons of problems like that. So the way it works is the following. It will, for example, generate all the spin states, and then it will give you a menu. Like that's an interactive version. So you can run it in, there's two modes. There's the like local mode where you just tell it start and the end and don't bother me. So then it will make those assumptions. But the interactive mode, which is the one that we use the most, and there's a little switch, it will stop and tell you like, okay, so do you want the triplet or the singlet, or do you want them all, or do you want this or that? And so therefore it's very smart generating all the possibilities. And we have software tools also to check that these things are right. So there's a lot of checking that happens with tools and also with sub-agents that check other agents. And then we show the human every once in a while the choice. Choose your own adventure. And then you can tell it, I want you to do 1, 2, and 5, or whatever. Right?
Thank you.
So I'll tell you a story actually. I have a joint friend with Seth called Luca Turin. So he has a theory about the quantum theory of smell. It says molecules smell depending on the vibrational structure. So we ask it very cool things like, according to Luca Turing, will this smell the same as this other thing? and it calculates the vibration structure of the molecule, and it's not so sure that theory is correct, but it can assume the theory is correct and do all the comparisons. And there, it asks you many questions. It's like, do you want limonene or citronelle, or do you want this or that? And like, it's asking you all these odorants. So you can ask it very open-ended questions, and then it will start telling you which kind of molecules you want to use and so on. And then you choose the molecule, and then you choose details about the molecule, and you continue going down that pathway. Yeah. Yeah.
Yeah, thank you for your talk. I was wondering, so earlier you mentioned sort of this scaling law.
Nice to see you here.
Yeah, nice to see you here as well.
She used to be in Toronto, by the way. Yeah.
Yeah, so
In
you
the lab.
talked about the Aspuru-Guzik scaling law of agents in relation to the number of tools they have. I wondered if you saw something similar between number of agents total in your network, and if there is an upper bound to how many agents can communicate with each other to achieve the different goals.
I wish I knew that answer. The question is, what is the upper bound in the number of agents and tools and so on? I don't know. I think it can go pretty far. Eventually, I think things will get confused, right? Like, if you have, it just can go ridiculous. If you have 10 to the 7 agents or tools or something, I can imagine the machine learning models will really break at a certain point. I just don't know exactly where that point is. But in the hundreds of tools that we're using, we haven't seen any problems. Yeah.
I think we had a question here. Let's do maybe 2 more questions, and after that, we will also have a reception, so we'll take more questions there. So let's do a couple more questions.
Yeah. Thanks for the great talk. So I'm a postdoc with Rafa. It's nice to be here today.
Cool, nice to
So
meet you.
my question
Nice to
is,
meet you, grandson. Yeah.
my question is, where do you vision like the compute backend of this will be? Like the large language model part of these agents probably coming from the API access. What about the compute? Are they gonna coming from some cloud compute or some local hardware compute? The problem there is you did mention that it's hard to transfer some of these codes from machine to machine. For example, you showed that your agent is capable of submitting jobs to HPCs. It's probably going to be hard if I deploy it locally on my machine. I try to submit here on MIT cloud service. So how would you think about that?
Absolutely. So we have a plan for that, but it's very preliminary. So yes, correct. So the question is, okay, where is the compute happening? Our first model will be, you will connect to us in the cloud, and thanks to Jensen Huang, my new overlord, I have some credits that are for free. That will give to especially people in the developing world and in Latin America, and not to you in MIT. I'll give you less, but there will be some free credits. No, because you're here in MIT and Harvard and whatever, right? So, but anyway, these credits will allow you to like go and explore the system, and then if you want more, then you pay us, and we'll pay the cloud providers. That's the life. Because I'm an academic, so you'll pay your own compute. Now, what you're talking about, we call el Agente pirata, the pirate agent. So that one installs a sandbox in your desktop or your Mac or your cluster and runs stuff in the sandbox. So that's possible. Look at OpenClaw. It's just a question of security. Would you trust me to suddenly send you a sandbox? So we plan to develop this open sandbox agent that actually the Graphico guys already have a preliminary version of it in the lab where you can download the sandbox that has everything to your Mac. And then we prepare whatever to compute. And you don't even have to download the packages. You have a little image you can run in your computer or your cluster. So that's called Agente Pirata. It's not, I didn't tell you about it, but we're building something like that. For that reason, because you probably want to compute on-prem. But what we'll release soon is you pay for us in the cloud, and then, sorry, if your PI doesn't have money for that, Rafa doesn't have money, then he cannot use El Agente. Because I cannot pay for Rafa's research from Toronto. Yeah.
Hi, thank you for the great talk. So I was wondering, so you talk about a lot of using the AI agent to run QM calculations, but there's actually a lot of like parameters or decisions you have to make for different systems you're running into. And I think just having something run without error wasn't hard, but to be able to produce data that actually make physical sense. I think, sure, you could read the literature and find out, for a typical molecules, what kind of parameter you should set. But then I thought the whole idea of science is to do the computation on something that we haven't understand, we haven't explored, and the parameters you choose for those systems might be dependent on the system itself, which there's probably no data available online. So I guess my question is, how do you make sure that your calculation actually makes sense? And all the question is, I'm a PhD student and trying to know if I will be replaced at all by all of this.
The first thing I would say about the job replacement, let's start with that. That's the elephant in the room. We were worried about when PowerPoint came out and when the email came out and when typewriters came out, and people have always been worried about when a new tool comes out. I think, if anything, there will be more investment and more interest in AI-driven discovery if AI-driven discovery is faster. So I feel if you know how to use these tools, you'll be fine. But I also feel it's extremely important to be an expert for exactly that reason. Because if you use these tools as a black box and you don't know anything about it, it's like imagine the problem I mentioned. Alán, do a weather prediction. What is going to be the weather tomorrow in Boston? I imagine there's some open source tools from NOAA that I can download with Forjador and run a calculation. But I don't know those parameters. What is the grid size in kilometers, or what is the whatever parameter for the differential equation integrator? I don't even know what parameters those weather simulation models have. Right? So if you have an experimental chemist that never runs quantum chemistry and runs our tool, we will make sure with all those kind of things, like for example, reading Stefan Grimme's papers and things like that, that we'll try to give them the best solution possible, but the human is still an expert that when he gets a report, has to figure out if the report is correct. So this is a problem that we have in Agente Teórico. So Agente Teórico, I still know enough quantum computing to tell the postdoc, okay, so I think if we combine these three things, this is new, right? Like if you combine, shadow tomography with this and that, nobody has done that. I mean, it's still boring because it's just combining three different ideas in quantum information, but we're trying to do that. But there's no paper in the archive for that, so we're like, okay, let's generate a paper and then we can verify it. But we need a quantum computing guy to verify whatever this thing did. We don't have enough capability with the agents to verify yet. So your point is very well taken. You still need to know what's happening because we generate all this data about if he picked a parameter you don't like, because maybe the literature is very popular in the literature, but it's wrong. Then you have to kind of tell it. You know what? I just really don't like that. Okay? But you can tell it very sophisticated things like, why don't you read this paper and see what they did in this paper? And I think it should be more this way or something like that. And then it will try a different strategy. So those are the kinds of things that we're exploring. But I think the human in the loop is very important. I think we're cyborgs still, I'm saying. But eventually these guys become androids. But at the moment, we're cyborgs. We work with them together. As of today, yes.
Otherwise, they will start kicking us out of here. But before we do, we have an important thing that we need to do before we thank Professor Aspuru-Guzik, and that we are going to present him is a very special, not computational, but real glass beaker, which is made for Wulff Lecture. This is the prized possession that very few human beings get to have for our Wulff Lectures. It has been made here in a very real MIT glass lab that you all should visit. And we really appreciate your scintillating, your provocative talk.
Thank you.
Our reception will take place in the Chipman Room in Building 6, so enjoy a beautiful walk through campus to join us, and you will have an opportunity to ask more questions with our speakers. So let's thank Professor Aspuru-Guzik again.